Dear friends, this is a series of lectures in which we will discuss on linear transformations.
If x and y are two non-empty set, then obviously we can construct maps from x to y. Okay. So for example, we can easily construct a map, constant map. So if this is a set x, okay, and this is the set y, so obviously there is a map that is a constant map from x to y. That is all elements of x goes to some constant of y. So yes, so easily we can construct a map from x to y. Okay. So now if we impose some additional algebraic structure on x and y, then we are interested to study some typical type of maps from x to y. Okay, so in this discussion we will consider that x and y are both vector spaces over the same field f. Okay, let us take two vector spaces v and w over the same field f. Now we are considering those maps from v to w which preserves the algebraic structure on v. So now we are going to define the formal definition of linear map. So linear map are maps which preserve the algebraic structures on the vector space V. Okay. A linear transformation T from a vector space V over the field F to another vector space W over the same field F is a map which satisfies the following properties. The first property is T of alpha plus beta is T alpha plus T beta, where alpha and beta are two vectors from the vector space V. Okay. The second property is T of some scalar multiple of alpha is C of T alpha, right? Where C is a scalar from the corresponding field and alpha is a vector from the vector space V. Okay. The first remark, we observe that T of C alpha plus d beta equal to T of C alpha plus T of d beta. Okay, and this can be written as C of T alpha plus d multiplied by t beta. Okay, where C and d are two scalars and alpha and beta are two vectors. Okay, so we can restate the definition of linear transformation as follows. A linear map T from a vector space Vf to another vector space Wf is a map such that T of C alpha plus d beta equal to C multiplied by T alpha plus d multiplied by T beta. Okay, where C and d are scalar and alpha comma beta is are vectors. Okay, this definition is equivalent to the definition that we stated previously. Okay, so next remark 2, if V is a vector space over the field R, okay, then by line Lx where x and y are two vectors from the vector space V, we mean the following set. Lx is the collection of all vectors from the vector space V such that those vectors can be written as convex combination of x and y. Okay, where the scalar t lies between 0 and 1. So this is called line segment in the vector space V over the field R. Okay. So first observation, T is a linear transformation from the vector space V over the field R to another vector space W over the same vector field R. Then we see that T of 0 equal to 0, because T of 0 can be written as T of 0 plus 0, that is actually T0 plus T0, right? So from this it follows that T of 0 equal to 0. Okay, and also T of z is equal to T of 1 minus Tx plus Ty, and this is nothing but 1 minus T into Tx plus T into Ty, because small t is a scalar quantity, right? Okay, so geometrically a linear map sends a line passing through origin to the line passing through origin or the point origin. Okay, so now we demonstrate some simple properties of linear transformation. Okay, let T is a linear transformation from the vector space V over the field F to another vector space over the same field F. Okay, then T of 0 equal to 0, because you know that T of 0 can be written as T of 0 plus 0, and that is nothing but T of 0 plus T of 0, and from this it follows that T of 0 equal to 0. So origin goes to origin. The next property is T of minus alpha equal to minus of T alpha, because you know that T of 0 can be written as T of alpha minus alpha. So that is actually 0. It can be written as T of alpha plus T of minus alpha, right? And from this it follows that T of minus alpha equal to minus of T alpha. So naturally we can write T of alpha minus beta equal to T alpha minus T beta, where alpha beta belongs to the vector space V. Okay.
Now we pose a question. Why do we consider the same field when we are defining a linear transformation from a vector space V to another vector space W? Okay. So in our next video lecture, we will demonstrate some example of linear transformations. Thank you.